Okay, now we're back for 11.5, which is about alternating series. Uh, Before I get into it, though, let me just make a statement about what we did in the previous one. Let me emphasize that the comparison tests from last time only apply for positive term series. So your sums cannot involve any negative numbers, or at least after some point you only have positive numbers. If there's a few negatives at the beginning, that's no big deal because you can ignore those as far as convergence goes. Convergence or divergence. All right, so alternating series are a little bit different. Those are series where the terms alternate positive and negative. So for example, if we had 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 and so on, if the signs are alternating, every other sign is positive and every other sign is negative. That's an alternating series. This particular one would be, well, the formula for the numbers would be 1 over n, but we have this alternating sign that looks like negative 1 to a power. Let's see, which one is it? If we start with n equals 1, the odd terms are positive, the even terms are negative. So I need to have n plus 1 or n minus 1 up here. Doesn't matter which. Because when the exponent's even, I get a positive. So if I want it to happen for odd n's, I have to add a 1 to n to make that even. Okay, so this example is called the alternating harmonic series. And so we want to come up with a way of determining whether or not an alternating series is convergent or divergent. Okay, so first let me be a little bit more precise with my definition. An alternating series can be written in the form where you've got this negative 1 to a power, and depending on the even or odd, like which terms are even or which terms are odd, you can either have it negative 1 to the n or negative 1 to the n minus 1 or n plus 1. But the key thing is the other part, bn, where bn is positive. If bn was negative sometimes, then this minus 1 is not really doing all that much. It's not determining the sign of your terms. So you're separating out a positive part and an alternating sign part, essentially. Okay, so we're looking at series that look like one of these two. And they have their own test. So the alternating series test. All right, so if your sequence of b's, whatever you start at, whatever n value you start, your sequence of b's is decreasing and the limit of the b's as n approaches infinity is 0, then your alternating series, negative 1 to the n times those bn's, must be convergent. And here when I write negative 1 to the n, there's nothing special about that. If I put n minus 1 as my exponent, it's still true. So the point is, if you're looking at an alternating series and you just consider the positive part of the term, so forget the alternating part, just look at the positive part. If that sequence is getting smaller, is decreasing, and the limit of that sequence is 0, then the alternating series has to be convergent. Okay, so let's look at our example, our first example. So the alternating harmonic series that we already looked at. What I look at is 1 over n. I forget the minus 1 to the power. Just look at the positive part of this term. 1 over n, that sequence, two things. Its limit as n approaches infinity is 0. That has to be true. That needs to happen. And by the way, if that fails, if you check the limit of this and it's not 0, then you can say that the series has to be divergent by the divergence test. Because if the limit's not 0, the sum can't converge. So it's best to check the limit of the bn's first, because if that fails, you're done. All right, but we're not done. We can't say converge yet. If the limit is 0, that doesn't tell us that it's necessarily convergent. For the alternating series test, we also then have to check, is this a decreasing sequence? So is it decreasing? Well, you can see it that if n gets bigger, this fraction gets smaller. But let's think of it more formally. 1 over n and 1 over n plus 1. That's like two terms of this sequence, two consecutive terms of the sequence. If it's decreasing, the earlier term has to be bigger than the later term. Well, this one has a larger denominator, so it's a smaller fraction. So 1 over n is bigger than 1 over n plus 1, which is then bigger than 1 over n plus 2, and so on. So yes, it is decreasing. So we've checked the two requirements of the alternating series test, so that tells us this is convergent. Okay, this is in contrast to the regular harmonic series, the summation of 1 over n. If I did not have the alternating part, summation of 1 over n is divergent. If it's alternating, it's convergent. So that tells us that it's easier for a series to converge if it's alternating. It's easier for an alternating series to converge than a positive valued series, a positive term series. Okay, so on that note, let's look at alternating p series. So let me do the same thing, but with 1 over n to the p. This is an alternating p series. So let's go through the alternating series test. Now, as n approaches infinity, what's happening in this denominator? Well, it depends. If p is a positive number, then there truly is a denominator here. There really is an n in the denominator. But if p is negative, then a negative number here will actually move this n into the top of the fraction. And as n grows to infinity, I would get infinity. So this limit will equal 0 if p is greater than 0. Let's see, if p equaled 0, that'd be a silly sequence. But if p equaled 0, this would just be 1 everywhere. So I'd get 1 if p equals 0. And I would get infinity if p is less than 0. So, of the possibilities, the only one that is going to matter, the only one that doesn't fail, is when p is greater than 0. We get a 0 as our limit when p is greater than 0. If p is less than or equal to 0, the first this part of the alternating series test fails, or in fact the divergence test fails. All right, so then if p is greater than 0, that's all I need to check now because that's the only one that worked in that step. If p is greater than 0, what is this sequence? What happens with this sequence? Well, let's again compare two consecutive terms, 1 over n to the p and n plus 1 to the p. Well, again, this has a big, if p is positive, n plus 1 to the p is bigger than n to the p. So 1 over n to the p is the larger of the two fractions. So the sequence is decreasing. And by the way, when you're checking for decreasing, sometimes it's easy to figure it out just by comparing consecutive terms like this. If it as the sequences get more complicated, there's always the possibility of, if you replace n with x's, can you take the derivative and see that it's negative? It's just not really worth it on these simple examples here. So it is a decreasing sequence. So for this sequence, for this type of sequence, we have verified the two requirements for the alternating series test in the case where p is greater than 0. So our rule is alternating p series are convergent if p is greater than 0, and they're divergent if p is less than or equal to 0. So go back and compare that with the regular p-series test. Those, if you don't have the alternating aspect, those were convergent when p was bigger than 1 and divergent if p was less than or equal to 1. So like I was saying, more of the alternating ones converge than the ordinary p-series. It's easier to converge if you have the alternating signs in your terms. Okay, so let's say a little bit about, actually let me think for a second. Yeah. Let's do a couple more examples, and then I'll say a little bit about why the alternating series test works. Okay, so let's do this one. Negative 1 to the n times n over 2 to the n. N equals 0 to infinity. All right, so we look, it is alternating, so we can try the alternating series test. Like I said before, when you're doing the alternating series test, first check the limit of the positive part. So limit of n over 2 to the n as n approaches infinity. If this is not 0, we can say the series diverges. If it is 0, then we press on and check the decreasing part. Whereas if you check the decreasing part first, and it's not a decreasing sequence, or it's not always decreasing, that doesn't tell you, it's inconclusive. You have to abandon the alternating series test, but then you don't have an answer. You have to find some other method. Anyway, it's usually easier to check this limit anyway. So in this case, as n goes to infinity, this is an indeterminate form, infinity divided by infinity. So let's use L'Hopital's rule. I'm not going to bother switching out with x's just because it's not worth it here. I want to take the derivative of these numbers with respect to the variable n as if it was x. Derivative of n is 1. The derivative of the exponential function 2 to the n is 2 to the n times ln of 2. Right. So now as n grows to infinity, we have 1 over 2 to the infinity is infinity. That's 0. That's not indeterminate. 1 divided by infinity, that's 0. So our first part is satisfied. The limit is 0. Now we have to ask, is it a decreasing sequence? So this is more complicated than before, so let's actually do a derivative method. So let's write the function f of x equals x over 2 to the x. I want the derivative of that. Let's write this as x times 2 to the minus x to avoid the quotient rule. F prime then is the product rule. Derivative of x is 1 times 2 to the minus x plus x. Derivative of 2 to the minus x would be 2 to the minus x ln of 2 times the derivative of the inside function, which is negative x, so times a minus 1. Let's factor out 2 to the minus x. All right. So now the question is this a decreasing function? Well, it's decreasing whenever the derivative is negative. And 2 to the minus x, that part's always positive. Exponential functions are always positive. 1 minus x ln 2, that's not always negative, but it will be pretty soon, for eventually. So if x is big, so in particular, if x is 1, we have 1 minus ln 2. No, sorry, that's not quite enough. Ln 2 is less than 1. Yeah. If x is 2, you can type this into a calculator, but maybe I should better do that. 1 minus 2 ln 2, that's negative. So this here is negative if x is at least 2, because if x is bigger than 2, I'm subtracting even more here. So we can say, even though this is not really, it's not a decreasing function everywhere, it's decreasing once we get past x equals 2. So it's eventually decreasing. And one point that I should really emphasize more is when we're talking about convergence or divergence of a series, it doesn't really matter what's going on at the beginning of the series. It's all about what's happening in the infinite part, the never-ending part of the series, the part that goes on forever. So if I were to ignore the first few terms of this series, that won't affect the convergence or divergence. That's just slicing off 1 or 2 terms. So I can apply my alternating series test to the series that starts with n equals 2 here. It converges because the function is decreasing on that interval. So in other words, eventually, answering a question like, is the thing decreasing? And if you answer it by saying, yes, eventually, that's good enough. So yes, it is decreasing. So that tells me the limit's 0. It's ultimately a decreasing positive part. So by the alternating series test, this is convergent. All right. Let's do one more. So let's do this one. -1 to the n over n factorial divided by n to the n. I better start at 1. Otherwise, n to the n is a problem. Okay, so this one's trickier because of the factorial, and also the n raised to the nth power is a trickier thing to deal with. All right, but this is an alternating sequence, alternating series. So we can try to use the alternating series test. As I've been saying, it's generally preferable to start by asking what the limit of the positive part is. I'm drawing a blank on whether or not we did this specific example already. Yeah, so let's use a squeeze theorem for this. The squeeze theorem argument. N factorial is n times n minus 1 times n minus 2 all the way down to times 2 times 1. N to the n, well, so first off, n factorial, that's n factors I've just listed out here. N to the n is also n factors, but they're just all in. So let's just think about this. N over n, that's 1. Those two things cancel. So this is n factorial over n to the n. N's here cancel. All these others are less than 1. N minus 1 divided by n, that's less than 1. N minus 2 divided by n, that's less than 1. So this is going to be less than or equal to if I just had one of these. So let's take the simplest one. 1 over n here. Because it's 1 over n, but then it's multiplied by 2 over n, times 3 over n, times 4 over n, and so on. Every time I put another one of those fractions, I'm multiplying by something less than 1. So this fraction is much smaller than this fraction. It's not, if n is big, it's much smaller. On the other hand, this is also a positive sequence. Both these things are positive, so this is bigger than 0. So n factorial over n to the n, it's trapped between 0 and 1 over n. Both of these sequences on the outside, they approach 0 as n grows to infinity. So by the squeeze theorem, the middle also has to go to 0. So this limit is 0 by the squeeze theorem. So that's the easy part. Now we have to argue that this is decreasing. Okay, now if I want to show that this sequence is decreasing, I can't use derivatives because of the factorial. There's no way to take a derivative of a factorial. It's not a function of x. It's a function of just whole number n's. All right, so we have to do this by looking at consecutive terms. We have n factorial over n. We want to compare that to the n plus 1 version. So let me leave some space in between here. N plus 1 factorial divided by n plus 1 to the n plus 1. I replaced all my n's with n plus 1. So this is one term. This is the next term in the sequence. Okay, so what I want this to be decreasing. So with n plus 1, that should be smaller than the version with n. Now, I can't directly see it, though. This one, the n plus 1 factorial, that's bigger than n factorial. So the top of that fraction is bigger than this fraction. The bottom of this fraction is bigger than the bottom of this fraction. So that means this fraction wants to be smaller than this. But again, it's two competing urges. We can't see directly which one wins out. So what we need to do is a trick. There's more than one way I could do this, I suppose. I guess we could do it like this. Let's simplify this. N plus 1 to the n plus 1. That's a bunch of n plus 1's multiplied. N plus 1 factorial, that's n plus 1 times n factorial. So what I'm going to do is I'm going to cancel an n plus 1 from the top and the bottom. That'll leave me with n factorial on the top and n plus 1 to the n on the bottom. So that's just cancellation. I've taken off that biggest factor from the factorial, and I've canceled it with one of these n plus 1's from the bottom. Now they're closer to each other. They're more comparable. They have the same numerator, but this one, n plus 1 to the n, that's a larger denominator than n to the n. So this fraction will be smaller. N factorial over n to the n is bigger than n factorial divided by n plus 1 to the n, which is the same as the next term in the sequence. So therefore, yes, it is decreasing. So by our two requirements of the alternating series test, this is convergent. Okay, so I'm going to let me write down one more thing to make sure you take note of it. So I've said this multiple times, but let me write it down. If you're trying to apply this test, if the limit of the bn's is not 0, that tells you divergent. That's just the divergence test from a few sections ago. If bn is not decreasing, now, so again, let's be clear here. Not decreasing doesn't mean increasing. It means your sequence could be going down and up and down and up and down and up. So it could be something like that. If that happens, it doesn't tell us that it diverges. It's inconclusive. Inconclusive. Okay. So if it's not decreasing, this test just doesn't work. You have to use a different method. And at the moment, we don't have another method that would work for an alternating series test, alternating series but we will in the next section. Okay, now if Bn is increasing, then it's actually going to turn out that the limit's not 0, so you'd have divergent. Because Bn's are positive. If they're increasing, they're not going to approach 0. All right. So the remaining thing I want to talk about is, well, there's two things, but they're going to have the same discussion, so they come from the same discussion. I want to give you a brief explanation for why this works, why the alternating series test works, and at the same time I'll tell you a little bit about how you can approximate the value of an alternating series. All right. So why does the alternating series test work? So let's suppose the Bn's approach 0 and they're decreasing. Then let's look at, this is just going to be a proof by picture. Let's look at one of these alternating series then. -1 to the n times b to the n. I want to look at the partial sums. So I'm going to draw a picture of a number line here. All right, so this is, remember the partial sums are, I'm going to add one term at a time to this series, to this sum. So I add the 0th term. When n is 0, I have -1 to the 0, that's 1, b to the 0. So b0 is a positive number because our sequences of b's are positive. So it's going to be somewhere out here. So that's b0. Let me label it b0. But in particular, this is S0. This is the 0th partial sum. Okay, so then you look at the next partial sum. Well, that's going to be the S1. I would take S0 and I'd add the next term of my sum. So I have B0 plus -1 to the 1, B1. So basically I'm subtracting B1 from this. So my next partial sum will be somewhere to the left, but since the b's are decreasing, I won't make it all the way back to 0. I'm subtracting b1 from here, so that'll put me someplace in between, maybe around about here. This would be b0 minus b1. So in particular, this distance here is that's b1. So that's S1. Then S2, I would take this and add the next term, which would be the second term, -1 squared, that's plus again, B2. So I'm going to be going to the right. I'm going to add something on, and I'll end up someplace to the right. But again, it's a decreasing sequence of B's, so B2 is smaller than B1, so I won't make it all the way back to S0. I'll make it somewhere in between, so we'll say here. This would be B0 minus B1 plus B2. I'm going to stop labeling that top part. This is S2. And this distance, that's B2. So if we keep this up, as I keep adding more and more terms, I'm switching direct, I'm going back and forth. But I'm going back and forth at decreasing distances. So S3 is going to be someplace to the right of S1 and to the left of S2. And then when I add B4, I'll get S4, it'll be someplace here. and S5 will be someplace here. I'm gonna be ping-ponging back and forth, but the distance between two consecutive partial sums is shrinking. So what's happening is I get two sequences out of this. I get a sequence of odd partial sums that are increasing, and I get a sequence of even partial sums that are decreasing. And both of those halves, both of those sets of partial sums are monotone sequences, and they're bounded. The odd partial sums are bounded above by really any of these even partial sums. So it's a ceiling. The even partial sums are bounded below by any of the odds. So what we can argue then is by the monotone convergence theorem from a couple sections ago, a monotone bounded sequence has to converge, has to have a limit. So basically these two sides have to meet in the middle somewhere. And the place where they meet, that's the value of our sum. So our alternating series converges to some place in the middle here. Okay, we don't know where, but the limit has to exist because of this behavior where they're closing in from both sides. All right, so let me keep most of this picture here. You don't need all the labels though. We can use this same argument to talk about approximating an alternating sum. So we can see this. Let's think about S4 here. We know the actual value of this infinite series has to be somewhere between S4 and S5. Right, so it has to be somewhere in between these two. Well, this distance, that would be B5. So what that tells me is if I tried to approximate the value of this infinite series by just adding up the first four terms, or from 0 to 4, so I took S4, I would know that the farthest I could be from the answer would be the next term in my sequence, B5. So I'll write that down. So I don't want to say this. In the same situation where BNs approach 0 and they're decreasing. If I add up a finite number of terms here, so I stop at the kth term, this will approximates the value of the infinite sum within B k plus 1. So the next B after I stop, that's going to overshoot. If I add or subtract that, it's going to overshoot the actual value of the infinite sum. Okay. So we're not going to be using this, but let me just illustrate this with an example so you see it. So let's do a concrete example. Suppose I wanted to approximate summation of -1 to the n minus 1 times 1 over n squared plus 1. Let's go from n equals 1 to infinity. All right, so we could check that this does converge by the alternating series test. The fifth partial sum is, well, I'm just going to add the terms that from n equals 1 to n equals 5. So let's see. When I plug in an odd number here, I get an even power, so my odd terms will be positive. So my first term will be 1 over 1 squared plus 1, so that's 1/2. My second term I'll be subtracting. So when n is 2, I have 1 over 5 plus when n is 3, I'll have 1 over 10 minus when n is 4, I'll have 1 over 17. Then my fifth term would be 1 over 26. Okay, so if we add these, we get approximately 0.37964. So that's, when we do this, that's always in some sense an approximation of the answer of the infinite sum. But we can be more specific. We can say, how good of an estimate is this? Like, what is the how far off could we be? So this is within well, we think about what would the next term be. Well, we stopped at 5. If I plug in 6, I get 1 over 6 squared plus 1. That's 1 over 37. That's it, within 1 over 37 of the actual answer. And we can say more than that. So my answer, so say this is S. S is between, well, since we just, the last one we stopped at, we added that. The next one would be less than that. So the most this could be would be this answer. So the smallest it could be would be this minus 1 over 37. Because that, when I do the next term, I'm subtracting 1 over 37. That's going to overshoot my answer. So the actual answer is between where I'm currently sitting in my sum minus the next term in the series. So the actual value is in between those two things. Okay, so then if you knew you needed to have a certain degree of accuracy with your approximation, like I wanted to be within 0.00005 of the answer, then I just need to ask, how big do I need to make n to make this smaller than that desired degree of accuracy? Okay, so we're not going to be using that, but I wanted you to see the approximation technique with alternating series. All right, so I will post a list of problems from section 11.5. It'll just be about determining or using the alternating series test to show a series converges, an alternating series converges.